So first and foremost, I am going to get a mic. I know a few people have mentioned it's hard to hear me at times, so I am on top of that, I promise. It will be soon. Second of all, for today's video, and something I'm really excited about testing, we are going to be testing distributed inference using vLLM. Now, the setup that I'm going to show today is a multi-node, multi-GPU setup. Now, essentially what that means is that this computer behind me is a single node with multiple GPUs, and the computer down here that you can probably only hear right now is another node with multiple GPUs. So the whole idea of today's video is that these computers are actually going to be running the same LLM, however they are running it together. So all four cards among the two separate nodes are going to be working to serve the same model, which I think is something that is extremely cool in a world where you need a lot of VRAM to run some of these larger models. So instead of having to worry about shoving a bunch of cards into one motherboard and getting a Threadripper for PCI lanes or something like that, you can actually go ahead and use multiple different systems, which allows a bit more experimentation and freedom, if you will. Now, as this is a bit more of a technical demonstration, I think the best way to get into it is to quickly give a higher level overview of the documentation of what we're actually doing here. Now, to do that, we have the vLLM documents open, and in specific, we have the distributed inference and serving document. Now, this is a bit technical and sort of difficult, and I figure I'll just try to break it down to apply to what specifically is going on in my example. Now, we can see here how to decide the distributed inference strategy. And if we scroll down, we see something multi-node, multi-GPU, or tensor parallel plus pipeline parallel inference. Now, it can get a little confusing to specifically use these terms to refer to what's going on, but essentially, if our model is too large to fit on a single node, a node being a single computer, you can use tensor parallel together with pipeline parallelism. The tensor parallel size is the number of GPUs you want to use in each node, and the pipeline parallel size is the number of nodes. So essentially, to put it simply, I have two computers with two graphics cards in them each, and I would like to use them all together, which in this case would lead me to the multi-node, multi-GPU distributed inference setup. Now, if we scroll down here, there's just kind of some demonstrations on how to do this and things like that. It is a little difficult to set up, but I would like to just kind of show it here right now live. So first off, I have three terminal windows open with three different themes just to make it perhaps hopefully a little less confusing. So first, I'm going to connect to the head node. Okay, I had to switch the terminal window because the silver aerogel was kind of hard to see the text. So what I'm doing here is connecting to the first computer, which is going to be named the head node. And I have a conda environment to run all this. It specifically mentions here using Docker, which I'm just not going to do for this purpose, but there is a good reason for that, and that's that basically the environments need to be identical on the machines for this to actually work. So there are some considerations in terms of that. But now I am just going to activate the conda environment. It's just called myenv, so I know that's like super basic, and you're going to be like, dude, what are you doing? Like, that's embarrassing. I know, I get it. But, and now I am connecting to what is going to be dubbed the worker node. And you can see that I'm essentially just doing the same thing. So now that this is all set, I do have a list of commands here. And the first thing I am going to do is to export these specific environment variables that are going to be needed, as well as the command to actually start this. Ooh. I've made a mistake. Okay. Basically what happened there was that it was running from before when I was testing it, so there was a bit of an issue. But now I can go ahead and do this. So the command for the head node, which we'll get into a little more things like that later on. However, now I can add another node to this array cluster, which is exactly what we want to do to be able to actually get the distributed inference running. So all I have to do is array start address and the address of this head node with the specific port that is going to be used. So before I do that, I will export the environment variables necessary for the worker node. And one thing I do quickly want to note here is that when we see the sockets in here, where it's mentioned twice, it's vLLM. Now, the worker node is actually connected to my local area network using wireless, and the head node was connected using Ethernet. So you actually have to specify that here. And there are actually some test scripts and things in here, the helper script. That's not the helper script. There's a sanity check script that allows you to actually make sure that everything's talking before you really go in and test it. So that is another consideration of this, is networking, which would make sense because they're interlinked. Communication bandwidth is important and things of that sort. So I have exported those environment variables, and then I am going to be doing this. And I'm also specifying a memory amount, which I don't know if I really need to do that, but I'm just specifying it to the available memory per card, which now looking at it, that may be wrong, but we're just going to keep going. So now our cluster is kind of connected. So on the head node, if I just type array status, we can see here that we have two nodes connected. One is the head node, which is the water-cooled machine, and then this one is the dual 3060 machine. And if we go down here to usage, we can see that we have 4.0 GPUs available, which corresponds to the 2 GPUs per single node, so for a total of 4. And we don't really have to do anything here, but if we type the same thing down here in the worker node, we see we kind of get the same output. Now, the next thing I'm going to do is actually serve the model, which for the case I'm using here is Microsoft Phi 3.5 Mini Instruct. Now, those of you with keen eyes may be like, dude, you can run this on one card. What the heck are you doing? I get that. And I just wanted to use a small lightweight model to see how everything works here and gets configured and things like that. So before I try some large beefy model or something like that, I just wanted to get it working with something simple. So I'm going to run this, and it's going to go through and we'll get some terminal output and things like that. And then eventually we will start seeing, I guess you could say like status updates or something like that. So it is loading weights and things. And now there is actually something that I could show real quick. So here are the commands I'm running, and we see here GPU memory utilization 0.5. So that is the maximum amount of card memory that I am allowing vLLM to utilize per card, which in this case would be 50% of the card. Now, something I've noticed, and I'm not quite sure if it's something I've done or something like that, is that it is just basically using 12 gigabytes. So it almost seems to be defaulting to the VRAM allocation that the weakest node has, which would be the 3060s with 12 gigs. So I'm not sure if there's a way to get a powerful node to use more of its VRAM and a weaker to use less. However, I actually don't really know that this is designed to be used with non-homogeneous setups, meaning different graphics cards in different nodes. But now that that's done, I'm simply going to send a test prompt to this from my actual Mac Mini, which is what I'm doing all the screen recording on right now. And once I do this, you can see here that it is working, and it has given us a response. I'm sending it to the model, write me a short story about a robot learning to paint, and tells me Aiko, the robot, and blah, 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 okay? So understand that this looks pedestrian at first, but we can now extrapolate this a bit to what actually just happened. And honestly, I'm just gonna grab this and show you in person. So basically, here's where we were screen recording. And now we have this little guy here who I have dubbed Fanitarius, because it has the big fan in it. Don't ask. But we can see that the cards are each using around 6 gigabytes, and we can see the process here, the Ray Worker wrapper. And now if I head on over to here, which is scaled up to 300%, we can see that each of the cards are also using that same amount of memory. So essentially what is going on here is that this model is being served using both of these computers as a kind of cluster, which I think is really cool. So the actual response is coming from all 4 of these GPUs across 2 of these computers. So the model is actually spread out amongst 1, 2, 3, 4, which I think is just incredibly cool. And the fact that this one's on Wi-Fi and that one is on Ethernet is just, if you're like me, you're gonna be like, hey, this is actually a really quite cool thing that is capable of being demonstrated at home. All right, because I don't want the video to just be like a total whole screen recording thing, I am going to set something up that I bought specifically to allow me to experiment more with this. So I got a TrendNet 8-port unmanaged 2.5G switch, and fortunately both of these computers have 2.5G capable network adapters built into the motherboard. So I'm going to set this up and I'm kind of excited about it, so I'll just kind of pop this in the middle of the video because it does adjacently relate to what we're doing right now. All right, after accidentally turning the power off, I'm happy to report that these 2 computers are at 2.5G. And you can ignore the yellow because my modem is slow. But they're linked, and that's good for what we're doing. So in conclusion, there are just going to be a couple of specific things I want to mention just as considerations if you're going to be wanting to do this yourself. And one of those things is where right here they specifically say that it's important to make sure the execution environment is the same on all nodes, including the model path and the Python environment and things like that. And again, it is recommended to use Docker to do that, which I didn't do. I just kind of made sure that both machines had identical conda environments and the same model path. You may notice that they do actually have slightly different names. So for this head node here, where it's just SLBBS without the 1 that is here, I just made a symbolic link so that as far as vLLM was concerned, they did have an identical model path. And the only other thing I want to really touch upon here, there's 2 things. One is that if you are going to play with this and want to have an LLM help you or something like that, I noticed that Claude and ChatGPT do not have a lot of relevant knowledge in terms of this specific implementation of basically distributed inference with vLLM. So you may have to almost go back in time a little and actually start like reading through GitHub issues and things like that to find your answer. And the other thing from that is that they even mention it here. So in this GitHub issue here, it is talked about how complicated network configurations can be difficult. So essentially, you can see that I have these environment variables that I was running in either of the terminal windows for that specific. So for the head node, I was using this, and the worker node, I was using this. Basically, what that means is when I type this command here, it will show me my network interfaces on this specific machine. And we can see on this one that it is connected to the rest of the network using this interface, so ENP3SO, and we can see that. So that's why that is set to this for the environment variables that I will run on the head node. And the worker node is using Wi-Fi. So we can see here that on this interface, the WLO1 is where it is has an IP address that it connect with the rest of the network. So that's why these are set here. Now, again, I don't actually know that like these memory limitations and things like that are things that I would have actually needed to set. This was just sort of an exploratory look into the ability to actually run models across separate computers at the same time without just having all of the cards physically connected to the same motherboard and processor and things like that. So I think this is really quite cool. And what actually sparked me looking at this is one of my friends and I were actually talking about running distributed LLMs and stuff like that. So I started looking into what options there were for this, and I stumbled upon this, and I think it is really cool. A bit difficult to set up, but possible, as we saw here. And of course, I'm only using Phi 3.5 mini, which is a model that either one of these nodes could run by themselves. However, it was just kind of to get something lightweight that they could both download pretty quickly and fit, and just to be able to test them. And again, just seeing the utilization in the NVIDIA control panel across both computers at the same time, and then actually being able to send a request like that from a remote machine and have them in conjunction return the answer, I think is really cool. So that's going to conclude my initial testing of the distributed inference, which I think was totally awesome. And now that I have this little decent speed switch, I am going to be able to explore more with this. I do believe I need to get some more system RAM in at least the 3060 machine. That has 32 gigs of RAM in it, and I should upgrade that, but the RAM slots are extremely close to some of the hard tubing that goes under the CPU cooler, and I'm like adamantly against ever doing anything with this loop again, so I'm almost afraid to do anything with this machine in terms of upgrading. So yeah, I have had a few people ask if I have Discord and things like that. I do actually have one. I don't really use it very often, but I will put the username on the screen right here. So until next time.